My name is Neil. This is Mark and John, and we'll be talking about breaking C++ applications today. And we're going to launch right into it. The talk today is really about looking for vulnerabilities in applications. And there's an enormous amount of material out there about finding vulnerabilities in unmanaged languages such as C. And most of the material out there really is C-centric. It's about finding buffer overflows in C APIs, integer overflows that wrap allocators, very C-specific stuff. And we're going to try and exclude that to a large extent today and focus on constructs that are specific to C++. I think about 2/3 of what we talk about today is in existing documentation. If you pick up a good C++ book and read every single page, you'll probably find it in there. Whereas about 1/3, hopefully, of what we talk today is novel and should be relatively new bug classes to you out there. So for those of you who audit applications for a living, we should get pretty deep in technical depth, and it should be good. As to exactly what we're going to go into, there's a couple things that we're going to talk about. We'll start with dynamic arrays and the security implications of that. We'll launch into C++ pointers and some of the things you can get wrong there. We'll talk about the STL. And, it's a construct that's relied upon by a lot of C++ programmers for additional security on top of, what you get with C. We'll also talk about the topic that I personally think is one of the most interesting today, which is exception handling and the security implications of that, and some interesting and possibly completely new bug classes related to exception handling. So a couple things that are sort of very basic to what we're going to be talking about today. We'll start really low. What makes a bug class a threat? And first off, it has to be a mistake that a programmer is likely to make when they're designing an application. If it requires them to type in 10 random characters that no one will ever type, it's not going to, it's not relevant. So it also has to be likely to escape detection in the implementation and testing of the application. And the more likely it is to escape detection, the more likely it is to appear in a production application and have security implications. If it doesn't crash at runtime, again, or usually it doesn't crash, then it's more likely to be missed in QA. So these are things like integer overflows and issues of that type that occur in corner cases or above certain ranges for input. Another thing is that there can be code that will absolutely be guaranteed to crash in an application that can be vulnerable. It just may be in a code path that is not exercised very commonly. So these are sort of logical oversights, exception handling blocks, error handling conditions, and so on. And I'm going to ask people in the audience who write C++ code for a living to raise your hand. I'm just curious to see. Okay, there's a fair bunch of you. Okay, so what we're bringing today really is a security perspective. All of us have written a fair bit of C++ code, but we don't do it professionally. So some of what we're talking about today, you should be nodding your heads, and some of it will be old hat to you. Whereas, a lot of the C++ developers that I talk to, the security implications of some of the mistakes that we'll talk about today may not be as obvious as the fact that it is a bad programming construct. So, and the fact that something is obvious, again, doesn't necessarily preclude the fact that it's going to be in software. Look at, the number of vulnerabilities that are related to simple API calls that, should have been fixed, years and years ago. So, bad programming is usually the default case, not the exception. Anyone who writes perfect code in here can get up and walk out right now. I can't do it. I don't think anyone else can. So, there is, even though there's technology such as Boost and so on that fix some of these issues, we'll talk about some of this stuff. I think there's a lot of relevance to the material we'll present today as well, and hopefully you'll find that as well.
Is this working? Cool. Okay, so the first thing we're going to cover is something we kind of touched on a little bit on a blog post before, and that's dynamic array allocation in C++. So real quick, C++ 101, basic, instead of using malloc and free like you use in C, you use new and delete to dynamically allocate objects. So this is kind of like your basic example of creating something and deleting something. So C++ also has dynamically allocated arrays, and these are similar to C arrays. They have similar semantics. The thing is that these use a different set of operators. They use what's called the vector new and vector delete operators, or array new and array delete operators. And they're different. They do different things than the normal new and delete, the scalar new and delete. And you can see at the bottom of the slide basically what that looks like. We're going to create an array of 42 people and then do stuff with it, and then we're done. We delete, and we use the brackets and text. So, well, the first thing to notice is that with the array new operator, you kind of have a classic multiplication overflow situation. You have an object of a certain size, and you times the number of objects. Generally, an attacker is not going to be able to control the size of the objects, but oftentimes they'll be able to control the number of objects if it's like a file parser or something like that. So this is kind of a classic multiplication overflow. The multiplication overflow is it'll allocate a small amount of memory, but then proceed to operate on a large amount of memory. So Visual Studio 2005 does check for this condition, and Michael Howard wrote a blog post about it, but previous compiler versions don't check for the condition, and G++ doesn't check for the condition. And also, it's important to note that even if there are checks for the condition in the code, you can still provide your own custom scalar or vector new operators that could reintroduce the problems. So the other issue we want to touch on is mismatching the vector and scalar new and delete. And this is sort of interesting because the compiler doesn't warn when you use the wrong operator. When you mismatch the operators, because it's your responsibility as the programmer to provide the context of what to do with the pointer. So, and it doesn't crash basically due to just how the bits happen to lay out, but it doesn't crash enough that people actually, if you like Google for this problem, people actually believe that they're equivalent effectively. And we covered this in one of our blog posts earlier. So what we're isolating is basically two problematic patterns. Using the array delete on a pointer to a scalar object or a pointer in the middle of array, and that's the less likely one. And then using the more interesting one is, or the more likely one is, using the scalar delete on an array allocated with the vector new. So to understand why this could be bad or why this is a problem, first we have to kind of look at how C++ dynamic arrays are implemented. And this, of course, is implementation dependent, but this is the mainstream way that Microsoft and G++ do it, basically. So what it does is when you allocate an array, it allocates one chunk of memory, and the first thing it puts in the memory is a D word, a count, the number of elements in the array, and then after that go the objects. So that's pretty straightforward. The reason it needs the count is because when you later delete the array, the runtime has to call the destructor of every object in that array. So it starts at the end of the array and walks backwards calling destructors, and then deallocates the whole buffer. This isn't true for primitive types like arrays of chars or ints because they don't have destructors. So there's two attacks we isolated. So the first one was accidentally using the vector delete instead of the scalar delete. Now this is a less likely mistake. You'd need a pretty rare code path for this to happen. But even though it's less likely, it's more dangerous of the two scenarios, because basically what will happen is the D word preceding the pointer that you pass to the delete to the array delete operator is going to be interpreted as a count. So basically it's going to take your object and go off into the end of memory and start calling destructors based on whatever happened to be there before. So you could if that occurred in code, you could definitely figure out you could definitely exploit it, especially if the object contains V tables, because in G++, it's gonna if it had a virtual destructor, it's gonna call that on each object in the array, and you're gonna end up it's probably gonna end up pointing it at just calling arbitrary data that you most likely control. Microsoft's a little different because it uses the virtual destructor. If there's a destructor, it uses the V table it only uses the entry from the zero offset element in the array. So the more likely mistake is using delete, using the scalar delete on an array. And basically, the way you make this mistake is you forget to put in the brackets. So the obvious consequence is that only one destructor is going to be called. So there's definitely obvious memory leak situations if because only one destructor gets called and there's X number of objects still left in the array. But there's a more subtle problem in that free is called on a pointer that was never returned by malloc. So, and I can kind of illustrate this on the diagram on the bottom of this slide. You can see that the malloc block includes the count field, but when the pointer actually gets back up to the runtime, the pointer you get is the address of the first item in the array. So there's a difference of 4 there if you use the wrong delete operator. So what happens is you have an off by 4 situation where the previous size will be the cur size slash flag. This, by the way, this is the glibc. Windows is slightly different, but the cur size will be interpreted as the previous size, and the count will be interpreted as the current size. So it depends a lot on the situation and the context of when this happens, but this can certainly be exploitable on glibc, and there's more information on our blog post. One thing to note is that if you control the number of elements in the array, you have a lot more freedom and exploitability, because you can set flags and basically truncate your buffer so that the next free buffer ostensibly starts, or the next buffer ostensibly starts in the middle of the data you already control. On Windows, it's generally not as interesting, because if RTL free heap is called, because one of the first thing RTL free heap does is verify that the pointer, or it checks to make sure the pointer is 8-byte aligned, and if it's not, it just returns out without doing anything. And you can see that in this situation, our pointer will necessarily not be 8-byte aligned because it's off by 4. So RTL free heap is used in many scenarios, but not all. The system MSVCRT pre-Vista utilizes a small block heap for small objects, and those functions are vulnerable. Also, for bundled VCRTs, it depends on the active heap parameter. So it defaults to system heap on XP, but what you want to see is V5 heap or V6 heap.
Okay, the next thing we wanted to cover is pointer fun with C++. Now, obviously, memory corruption has always been a big issue, and it's talked about ad nauseum in C, and all those things are just as important in C++ code as well. But C++ has some additional things that basically add to the complexity. Basically, the C++ language allows additional scenarios that can cause memory corruption, and there's also additional complications, effects when trying to exploit such conditions. Now, there's actually a huge number of these, and we only have a certain amount of time, so we picked out a couple of them that we thought would be the most likely or most interesting, and we're going to go through some of those really quickly. So the first thing is shallow copies. So anyone who does any amount of C++ programming probably knows about shallow copying versus deep copying. Basically, shallow copying is the bitwise copy of object members from a source object to a destination object, and that includes pointers. This is in contrast to deep copying, where the data being pointed to is duplicated, so that each object has a private pointer and their own private copy of the data that the pointer was originally pointing to. Obviously, if you use shallow copying, there's some potential problems there. Sharing pointers can basically result in multiple objects manipulating the contents of a single memory location. And this can lead to some sort of memory corruption or inconsistent state if two objects are both active at the same time. Additionally, if the two objects at some point decide to delete the same pointer, then you have a problem which is double delete, which is kind of analogous to a double free in C, which we'll look at a little bit more in a minute. And lastly, of course, you could have one object that deletes a pointer while another object continues to use it, and it ends up having a stale pointer. So when would this happen? Well, the most likely place for this to happen is in default functionality